So let's do the part 4 of the lecture 4. So this particular section is going to contain the math problem. So obviously this is going to be important for the next exam. And some of these guys are already covered in the laboratories. So I hope you feel a little bit more comfortable for this particular sections. So the first thing that we are going to do is talk about molarities, its concentrations, and molarity with a capital M is defined by the number of mole of solute per liter of solutions. So how many mole of the stuff is in every 1 liter solution. So we're gonna denote it with a square bracket, and that's same as the mole, the capital M. So if the square bracket contains H plus, so the concentration of H plus equal to means, I should probably put this thing as 2 molar. So if that's the case, then I have 2 mole of H plus in every 1 liter solutions. Okay, and the typical stuff that we actually use for this particular sections is concentrated and diluted solutions. The concentrated solutions, obviously it's really concentrated, means that you have high ratio of solute to solvent, and then dilute solution have a smaller ratio of solute to solvent. So the same volumes, but this one contains the smallest number of solute molecules, and that one right there have lots of solute molecules, lots of them, and that's concentrated. And typically I want to go from this one to that state. For example, like I don't like the sweetest drink, so I need to dilute. For example, if I go to McDonald's and the tea at McDonald's really sweet, right? And then I put the waters to actually dilute the sweetness more or less. I dilute the number of mole of sugar molecule that's dissolved in the water, iced tea, to my liking, so that I can drink it. So that process is actually called dilutions, and it's a process of preparing the less concentrated solutions from the more concentrated one by adding water. The water, of course, doesn't contain the solute, right? So by adding water doesn't increase the number of mole of solute, right? So that the mole of solute before the solution and the mole of solute after the dilutions doesn't change. So the mole of solute is conserved more or less, right? So how do I actually get the mole of solute? Is actually the concentration. For this particular case, the unit is m multiplied by the volume. For this things, I'm going to use the liter. So m times L is equal to m times L, because this concentration times the volume is going to give you mole of solute, right? So concentration of the concentrated solutions multiplied by the volume of the concentrated solution should be equal to the concentration of the diluted solutions and the volume of diluted solutions. If I were to use the unit m, because concentration is molarity, right? M, right? and then volume is in liter, is equal to ml, the same stuff but concentrated, diluted. So the I hope I'm not blocking these things. Let me just oops. So the example is if I have the 5 molar solution with maybe 2 liters, right? Then that's equal to whatever the concentrations, which we don't really know what it is, but I am going to add 3 liters to these solutions to make the total volume to be 5 liters. So 2 plus 3 become 5. Then what is the concentration here? So 5 molar solution, I have 2 liters of those. I added 3 liters of waters to make the total volume to be 5 liters. Then these concentrations, before the dilutions it was 10, right? And then after the dilution it has to be 10, right? But 5 liters makes these things to be 2 molar, right? 2 times 5, right? So before the dilution, the concentrated solution had a 5 molar concentrations, but after the dilutions, the diluted solution, the concentration become 2 molars. So this formula right here is fairly useful one. So I advise you to actually write this formula so many times that so you can actually stick that things into your long-term memories. Now, every time that you do the solution chemistries, sometimes it's really tricky, and then you need to actually think about some factors. So let me just actually talk about this several factors that I think it's kind of important. If the molecule B is not soluble, then the concentration of that insoluble solute or the insoluble material, the concentration is 0, right? Because it doesn't dissolve. So it's not in the water, or it's not in the solvent, right? Or it's not in the solutions. So if it's not soluble, then the concentration is 0. But this is kind of important, right? Because you already had this table of the precipitation table. Remember that from the previous videos? Those becomes useful. Now sometimes that even though that it dissolves, stuff sometimes dissociate too, right? So for example, the NaCl doesn't exist in water. It's Na plus and Cl minus. It dissociates into Na plus and Cl minus, right? So if I dump in 1 mole of this guy, you may actually end up with 1 mole of the Na plus and Cl minus. There is no NaCl concentrations there. And sometimes that if I actually have, let me just try to write out this situation right here. So that the solvent is 1 liter water, right? And then I dump in 1 mole of the Na2, SL4, right? 1 mole of that one. Then how much of this Na plus do I have? So Na2SO4 is soluble compound, so it's gonna go into the water and then it dissociate into the 2 Na plus and then 1 SO4 2 minus, right? So if I dump in 1 mole of this guy, I'm gonna have the 2 mole of the Na plus and then 1 mole of the SO4 2 minus. So the concentrations for the Na plus, oops, is actually 2 molar, and then concentration of the SO4 2 minus is actually 1 molar here. I hope you get that one. Alright, then the other case is sometimes that reaction happens. For example, that AB reacting with the CD that's inside of the water, right, AQ and AQ, which precipitate AD, and then you're gonna form CB, right? And then if all of these things are reacted away to form completely, to make this AD and CB, zero concentration here, zero concentration here, and then everything is converted into this guy, right? So you may be actually looking at the concentration of the CB minus, CB, or maybe that you may be actually looking at the CB concentrations, or maybe that you may be looking at the concentration of the C plus or concentration of the B minus, right? It depends on the case of the, you have to look at the periodic table. Does it dissociate, and then does it dissociate into 1 to 1 or the 1 to 2? Those type of stuff you have to be careful about. And also, not all of these guys may actually turn into the product, right? Sometimes half of these things is gonna turn into the product. So maybe that the half of these things may be left inside of the water. In that case, that you may be actually following the concentration of the AB instead of some other things. So it's really the case by case and of what you are looking at, what you're trying to measure. Those are the important questions when you actually solve the problems. Alright, so let's just try to solve this problem. So if I actually dump in 0.25 molar, 0.25 moles of the AgCl2 into the 1 liter, that's 0.25 molar, then what's the concentration of the Mg2 plus and then Cl minus? So if the concentration of that guy is 0.25 molar, then that's 0.25, and then that one right there, because it's 1 to 1 to 2, so it's 0.5, right? Okay. And I think you can do this one by yourself, so I'm gonna skip that one. So I didn't want to actually talk about these things. Maybe 1/3 of the chemist, not maybe 1/3, maybe 1/4 of the chemist is actually called analytical chemist. And you may want to know what they do. They are actually trying to figure out what's in the sample and how much is in the sample. Those are the questions that analytical chemists answer on the daily basis. So the job of the analytical chemist sometimes involves what is the concentration of mercury in the drinking water, or what is the concentration of the pesticide that's found on the eggshell. Those are important stuff, right? Especially that we eat eggs, that I want to know what I'm eating, right? So those are important questions, and that's what they're going to answer. The technique that they often use, two of those that we can actually talk about. One is the gravimetric analysis. This is a precipitation reaction that we talked about in maybe 2 videos ago. And then the other technique actually involves a volumetric analysis. That's a titration that we talked about in the acid-base stuff, right? So those two we can actually use to find out how much of the stuff is in the solutions. So So one is a gravimetric analysis, the other one is the volumetric analysis. One uses precipitation reactions, the other one uses titrations. So let's just go to the gravimetric analysis first. So let's just say that I know that I have a AgNO3 in my solutions, but I don't know how much is in there. So let's just, we don't know that the actual concentrations, but let's just assume that we have 1 mole of AgNO3 in that solution, right? And then I'm going to sprinkle the table salt, the NaCl, into that solution. If I actually put 0.5 molar NaCl into that solutions, right? I have 1 mole of this. I have 0.5 mole of that. Then how much of the NaNO3 that I can form was how much of the AgCl that I can form. The reaction is 1 to 1 to 1 to 1, right? The ratio is 1 to 1 to 1 to 1, right? So obviously not all of the AgNO3 is going to react, right? Because I have only 0.5 mole of that one. So 0.5 mole of that is going to react with 0.5 mole of this to form 0.5 mole of that, and then 0.5 mole of this, right? If I put 1 mole of the NaCl, then its reaction is 1 to 1 to 1. So for this particular case, oops. So instead of that, if I have 1 mole of that, right? 1 mole, then 1 to 1 to 1 to 1. So I'm going to form 1 mole of that and then 1 mole of that, right? That was the easy one. But if I had 2 mole of these things into the solutions, then how many more of that do I form and how many more of that do I form? Again, I only have 1 mole of the AgNO3, right? And then to form the AgCl, I have to have Ag plus and Cl minus, right? But I only have 1 mole of Ag plus. So maximum amount that I can form is 1 mole, right? So always goes with a smaller number. So 1 mole of that and 1 mole of this, right? It's 1 to 1 to 1 to 1, right? So I only use 1 mole out of the 2 mole of the NaCl, right? I hope you get that. Now I am going to go back to the original questions. If I don't know the concentration of that guy, right? And I keep putting the NaCl into these solutions, then I may actually form 0.5 mole of the AgCl and then 0.75 mole of the AgCl as I put more and more into it, right? And then all of a sudden it stops at some point. Say for example like 0.8 mole of the AgCl. After the formation of the 0.8 mole of the AgCl, it completely stops. Then I know that I'm putting the excess of that one. And the maximum amount is 0.8, right? Because we actually observe that 0.8 mole of the AgCl precipitate. Then that, because it's 1 to 1 to 1 to 1, this has to be 0.8 mole at the start, right? Because I put excess amount of the NaCl, right? So now that's pretty much how you actually figure out how much of the stuff in the solutions. That's called the gravimetric analysis, because I use the precipitation reactions. On the other hand, if I use the volumetric analysis, you're going to use the titration stuff that you actually do in the laboratories. So this particular case, that you're going to have to remember the two basic definitions. The equivalence point is exactly where the number of mole of H plus and number of mole of OH minus is exactly the same. Okay, that's equivalence point. End point is where you stop the titrations. They may be very close, but never the same. Okay, we're trying to get to the equivalence point. So we choose the indicator that the end point is closer to the equivalence point. Okay, that's what we are doing in the titrations. So when you start the titrations, maybe that you don't have these color solutions, but at the end point that your indicator may change colors, depends on the pH, right? And then that where they actually change the colors, that's where we assume that it's almost the same number of OH minus and H plus. That's where the end point really is. And end point is not exactly equal to the equivalence point, but equivalence point is exact place at OH minus, H plus, exactly the same number of moles. End point close to it, but it's not exactly the same. Alright, so a very similar situation with the precipitation reactions. We know that we have a solution that contains the HCl, but we don't really know how much. Then you just keep dumping the OH minus, right? So if I actually have the 1 mole of the H plus, then, and also that if I have 0.5 mole of the NaOH added to the solutions, then I'm going to form the 0.5 mole of the H2O, and then I'm going to form the 0.5 mole of the NaCl, right? But if I actually have 1 mole of that, one more of this and then 1 more of that, then I also have 1 more of the product too, right? 1 more of that and then 1 more of this, right? And then if I add excess amount of the NaOH, I still have 1 more of this and then 1 more of that, right? So I just have the excess amount of the NaOH, exactly 1 more here. So going back to the original questions, we don't know that this is a case where we don't know the concentration of the H plus or the HCl, but let's just say that if I add like let's just say that we don't know the mole we don't know that, but if I put 0.5 more of that one, then I started to form lots of water, maybe 0.5 more, and then I keep adding the NaOH. I may form 0.75 more, and then that I form the 0.5 more of the H2O. But at the 0.8 more, it completely stopped producing the H2O. Then I know that HCl, like here, initial concentration or the initial number of mole was actually studied out with the 0.8 moles. This type of problem, by the way, that don't try to work it out with the concentrations. Always think of it in terms of the how many moles of the stuff that you have in the solutions. Okay, I think that's probably the last useful comment that I can actually think of for this particular videos. I think this is good enough for this video.